Hello everyone, this is Dr. Schleith, and in this video I'll be going over all of the learning objectives related to an idea where we continue our study of dynamics and forces. This time we're going to look at um, building upon our work with vectors, force is a vector, and also the idea of moment of a force. All right. There will be a link to this video covering these slides. So if you queue up this assignment in Focus, you should be able to just click on the link that will sort of be here. And if you did that, you're watching these videos, unless you just sort of went directly to YouTube. Please keep a record, as usual, of all your work in a physics journal. Make sure to take pictures of every page of your journal and send me copies of that to my email by noon Friday each week, as usual. The learning objectives that we're going to focus on in this set of slides are: students will be able to add two or more coplanar forces. Students will be able to resolve a force into perpendicular components. Students will be able to define and apply the moment of a force and the torque of a couple. Students will be able to apply the principle of moments, and students will be able to state the conditions for an object to be in equilibrium. Let's start with combining forces. We know that if two forces are in a straight line, they're acting in the same direction. All we have to do is add them up. Now we do have to pay attention to the sign convention there. If one force is negative compared to the other one, then it's like adding the negative or subtracting them. But that's still pretty straightforward to deal with. When two forces are at right angles to each other, we're using Pythagoras' theorem to add those up. A squared plus b squared equals c squared. And we've worked with that idea a lot up to this point in the year. If there are three or more forces, we can connect the forces by adding them head to tail. And if indeed they make this triangle of forces that you see in the example down here, so here are three forces acting concurrently on an object sort of at the center, at the tail of each of those vectors. And if we just sort of move the vectors around, so you kind of imagine taking force 2 here and putting its tail at the head of force 1, and then taking force 3 and sort of translating that in space, and so its tail were at the head of force 2, you can see that these three forces actually make a closed vector triangle. And so that triangle of forces would just say, well, then those forces are all balanced out. There is no net force, and the object is in equilibrium. The conditions for equilibrium are that there's no net force acting on an object, which means there's going to be no acceleration as per Newton's second law, but we're going to, in a moment, define torque and moment of a force, and that's sort of another condition for equilibrium, that there's no net torque on an object either. If there were a net torque on an object, then it's going to rotate or spin. And so an object may move or sort of accelerate translationally in space, so move left to right or up and down, and for an object to change its motion, it's going to accelerate, a net force is required to do that. If we can draw a closed vector triangle, we can kind of show that all of the forces balance out to zero, so the net force would be zero, so it wouldn't accelerate in space. But that doesn't automatically disqualify a net torque. There could be a net torque acting on that object, and so it would start to sort of spin around, and then it wouldn't be in equilibrium. And so for an object to be in equilibrium, it has to have both no net torque and no net force on the object. That's just a good thing to sort of keep in mind, sort of this last bullet point down here. The conditions for equilibrium are: there's no net force, there's no net torque. We'll talk about torque in a little bit. Equilibrium. If we work out the resultant force on an object and find that it is zero, this tells us the object is in equilibrium, at least in terms of the net forces acting on it. If we know that an object is in equilibrium, we know that the forces on it must add up to zero. We can use this to work out the values of one or more unknown forces. So we can think about it sort of, either one of those ways. If we know that the resultant force on it is zero, then we know that it's in equilibrium. So we can just sort of add up all the forces and kind of prove, well, this thing isn't going to be accelerating because all the forces add up to zero. There's no net force, and so if F equals ma, and we can calculate that the net force is zero, then there's going to be no acceleration. We can kind of conclude that. If we know that the object isn't accelerating, say we're inspecting an object and we know it's not accelerating, then we can also conclude that the forces that are acting on it must add up to zero. In other words, it's an equilibrium. And so if we can identify forces that are acting on it, and we might suspect it would be moving, but it's not, we can sort of deduce, well, there must be some other force that's sort of balancing out these other forces. So sort of thinking about Newton's second law on both sides of that equation, we can either observe that there is no acceleration and deduce that the net force is zero, or we can calculate that the net force is zero, and then we know the object isn't going to be accelerating. Sort of think about it on both sides of Newton's second law. This is an idea which we've worked with a lot leading up to this point, and now we'll sort of reinforce that learning objective, being able to resolve a vector into its perpendicular components. So in resolving vectors, we have this idea of the independence of dimension, that we can sort of treat a vector which acts sort of in both a horizontal and vertical sort of direction. We can break that vector down into how much of the vector is moving horizontal, how much of it is moving vertical or acting vertical and horizontal. So in this figure at the bottom left, we can see that there's a force vector illustrated with a black vector there, and it would have components that act to the right, the force in the x direction, and components that act up, the force in the y direction, which they're showing with red and green vectors respectively. We know that with our trigonometry, we could consider some angle theta. So this figure on the bottom right corner, there's an angle theta here. There's a force vector shown in red. And the side adjacent to that angle is going to be sort of the value of it can be calculated as the force here, the hypotenuse force, times the cosine of this angle theta. That would be the component of that force that's acting in the x direction. The component of the force that's acting in the vertical direction could be calculated as force times the sine of the angle theta. And we know that sine is the sine of an angle is equal to the side opposite, sort of the magnitude of the side opposite over the magnitude of the hypotenuse. And so the side opposite would be this component here, the vertical component, and the hypotenuse would be this force vector F. And so just by taking the definition of sine theta equals opposite over hypotenuse, we can conclude that the side opposite should be force sine theta. If that's not clear, let me show that with a bit of working here. So considering this triangle in the bottom right here, let's think about it just using the trig definitions, the SOHCAHTOA. So we're considering a side opposite this angle theta here, and so we kind of want to say, well, where did this F sine theta come from? Right, this side here that is opposite. And so we can kind of call that, let's call it the y component of the force. If the force is F, then this would be the vertical or the y component. And so start with the trig definition. The sine of the angle theta, it's always the function of the angle. Because I'm considering the side that's opposite, sometimes students will have memorized SOHCAHTOA, sort of a mnemonic device to remember which ratio of sides correspond to which trig functions. And so, SOH, sine, the S in SO, of the angle theta is equal to opposite over hypotenuse. And so here we have the sine of theta equal to the side opposite, which I've called F sub y, the y component of force, over the force, which is the hypotenuse, right? The hypotenuse here is this force vector that they've labeled F. If I multiply both sides of this by F, then you can see that I've solved for this y component. I've made it the subject of this equation. And that's why they're able to label this vertical side as just F, which is, remember, the magnitude of the force here, the hypotenuse of our triangle, times the sine of the angle theta. Right? So force sine theta is the vertical component because it's the side opposite, right? So they've labeled this y component of force F sine theta, and likewise the horizontal component is the cosine function. You could use the cosine of angle theta equals F sub x over F and get this same one up here. So working with resolving vectors is a really important idea that we've seen previously, and it's one that we're still going to keep working with throughout the year. The center of gravity is important when we consider how the shapes of objects can really sort of affect their motion. And so as a simplification, we can we sort of think about the center of gravity of an object. And so the center of gravity of an object is defined as the point where all the weight of the object may be considered to act. We can find the center of gravity of sort of an irregularly shaped object by suspending a plumb line through it from different places, and the center of gravity is always going to be where sort of those lines intersect, because the weight of the weight always acts straight down, and so we can kind of see that a plumb line is going to sort of act straight down. And so by looking at sort of where those lines intersect, we'd be able to deduce the center of gravity for an irregularly shaped object. If it's a symmetrical object, like a circle, the center of gravity is going to be sort of where your intuition may suspect, right at the center of that object. Forces can make an object turn round. And I suppose this here is supposed to be sort of like a joke. Like, here's something that's more pixelated, but as we increase the number of pixels, it's turning round. So the turning effect of a force, if we apply a force to an object some distance away from a pivot, it can make that object turn round. The turning effect. And so we define moment of force as the perpendicular component of force times the distance to that pivot. And so that's really what we call a cross product. Note that if you apply all of the force already perpendicularly, then it's just sort of force times distance, and that's what we call moment. So moment of force is the perpendicular force times the distance to the pivot. So the further away from a pivot you apply a force, the more turning effect, the more moment you're going to have. The sine theta is what sort of captures the fact that only the perpendicular component of force contributes to moment. If you were to apply a force at some angle other than perpendicular, then it does become important that you take the sine of the angle theta between the vector, which is the distance vector here, and the force vector that you're applying. A component of force that acts sort of horizontal, either sort of pushes the wrench this way or pulls the wrench out that way, is not going to really contribute to the turning effect, right? So only that component that acts at right angles to the displacement, the distance there, is going to be a part of the moment of force and give a turning effect. Archimedes famously said that, which translates to, "Give me a place to stand and I will move the earth." Archimedes really understood this idea of leverage, that you could gain a tremendous amount of leverage by applying a force, a greater distance away. And if you look up the history of Archimedes and the Battle of Syracuse, you can see that the brilliance of Archimedes still stands to this day, and there's some interesting sort of history there surrounding his life. Some of my favorite quotes from Archimedes, this among them. "Do not disturb my circles," another famous quote and famous last words. I'll leave it to you to research that history on your own. The principle of moments is a pretty important one. It says, for any object that is in equilibrium, the sum of the clockwise moments about any point provided by the forces acting on the object equals the sum of the anti-clockwise moments about that same point. And so just a moment ago, we defined what moment of force is. It's a force acting a distance from the pivot. If we look at this example here of a seesaw, the pivot here, the fulcrum, is going to be, sort of this point where about the seesaw can pivot. We have a 500 Newton person that's 2 meters away from the pivot. Right, and so the force, the weight, the force due to gravity is weight of 500 newtons acting 2 meters away. We could say, well, there's 1,000 Newton meters of moment acting, sort of this person B over here would make the seesaw sort of spin in an anti-clockwise direction. And so we could calculate person B would be exerting an anti-clockwise moment of 1,000 Newton meters. Person A is not as far away from the pivot, And remember that the distance to the pivot is part of that equation. In other words, the further away you are from a pivot, the more moment of force there will be. This is why sometimes we just need a bigger wrench, to sort of exert enough moment to, untwist a bolt or something. So here we have a person that is twice as massive and therefore has twice the force of gravity, as 1,000 newtons of weight acting, but only 1 meter away. And so you can see that seesaw remains level because the amount of clockwise moment from person A, who would, if person B weren't there, that would certainly make that thing move clockwise. We just multiply the force, 1,000 newtons, times the distance, 1 meter, and we get 1,000 newton meters of clockwise moment. And we've already calculated that person B would have 1,000 newton meters of anti-clockwise moment. So we just sort of add up all of the moments that are acting in the clockwise direction, and we can set it equal to all of the moments that are acting in the anti-clockwise direction. And if those anti-clockwise moments are equal to the clockwise moments, then the object is in equilibrium. In other words, there's going to be no turning effect due to the moment exerted on either side of the pivot. Remember earlier that we sort of more broadly defined equilibrium as no net force, no net torque. The principle of moment sort of captures the no net torque part of that. Moment of force and torque can sometimes be used interchangeably, but we're going to really think about this as, the moment of like a single force, and we're going to define torque of a couple in just a moment here. So we're typically going to, in this course, consider like the torque of a couple. If we have two forces that are acting sort of on either side of an object, we have sort of a couple of forces there. But you can see that the definition here, when we consider sort of how we calculate the torque of a couple, it's one of the forces. And so in this example over here of sort of a person that's sort of twisting the lug nut on a tire there, there's forces from both hands, sort of one, and they're both going in the same direction. In this case, anti-clockwise. So they're doing what? They're loosening the lug nut there. One of the forces, F1, times the perpendicular distance between the forces, okay? So if we just thought about moment, it would be that force times the distance to the pivot sort of being at point B there in the center. So we really do have mathematically the same kind of a thing between the torque of a couple and the moment of a force. We're just going to sort of examine situations where there's two forces acting sort of this perpendicular distance away. And so just kind of consider this definition here on this slide, that when we consider the torque of a couple, there's going to be two forces that are acting, and we're only going to multiply one of the forces times the entire perpendicular distance between those two forces. Rather than, for example, considering both of the forces and only multiplying it by like half of that distance. So think about torque of a couple like this. Two forces acting on either side of a pivot, and to calculate the torque of a couple, it's very similar to moment of a force, in fact, identical. One of the forces times the perpendicular distance between the forces. Think of torque of a couple as producing a turning effect, right? Feel free to have some discussion related to these ideas. Whenever you're learning something and the vocabulary is very new, sometimes it's very helpful just to be able to sort of have a discussion about it, make sure that you're using the language right. So we want to show an understanding that a couple is a pair of forces, which tends to produce rotation only, right? Like we're loosening a lug nut, we're just sort of rotating that. Forces producing rotation, we have a single force, a turning effect, and moment of force, right? So it's sort of the example that we had earlier with a wrench. The bigger the wrench, the greater the distance is from the pivot. So you don't have to supply as much force when you have a greater distance to the pivot. And that's why a bigger wrench can make the job a little bit easier. We don't have to exert as much force to achieve the same torque. Define and apply the moment of a force and the torque of a couple. You can go back to the previous slides and make sure you have those definitions down. And remember that two forces, we have a couple and this turning effect, the torque of a couple. You all know where to queue up some sample problems. So if you find October, November 2009, paper 11, question 13. There's a good sample problem related to these learning objectives. And here's another one, and I will be sure to give you your quiz, which will also be related to this and other learning objectives we studied previously on Friday. The lab work for this week, we're going to repeat the pendulum experiment. This time we're actually going to repeat the time measurements 3 times at each length of string. And so rather than just sort of timing 10 oscillations, we're going to do that, but we're going to repeat that 2 more times. So we've got sort of repeated trials, repeated readings. So the procedure here is going to be very much the same as a few weeks ago when we did the pendulum lab. We're going to set up a pendulum and measure the length of the string. We're going to measure the time it takes the pendulum to oscillate 10 times and record that data. Record how long the string is, record the time for 10 oscillations. Then we're going to repeat that. We're going to set it in motion again and record 10 more oscillations, record that, and then do it one more time. So we're going to have 3 sets of readings at each length. What we want to do with those readings is calculate the average time over 10 oscillations. Then we're going to calculate the range. And so remember, the range is the difference between the highest value and the lowest value, right? So what is the range of our readings there? In order to determine the absolute uncertainty, one of the techniques to do that is to take half of the range of values. And so if we do repeated readings, we're likely going to have a range of values. And we want to report the absolute uncertainty as half of that range of values. In order to get the percent uncertainty, that's going to be the absolute uncertainty, which remember we get as half the range of values, divided by the average measured value. So once we have 3 readings, we'll be able to average them, and that will be our measured value. Even though we don't really measure the average, we've measured something 3 times, and we calculate the average. And so that would be the measured value that would go in the denominator as we calculate percent uncertainty. So remember, percent uncertainty is absolute uncertainty divided by the average measured value. And the absolute uncertainty is half the range of values. Once we've done that, we're going to calculate the time of one oscillation, t, and also calculate t squared. Include these values in a data table, also with the length of the pendulum string L. Then we're going to vary the length and repeat until we have 7 sets of readings. And so at 7 different lengths, we're going to measure the time of 10 oscillations 3 times each. And then do the calculations with the uncertainties as explained in bullet point 3 on this slide. Now, as I record this, I know that there's a window with my sort of head over there, and so maybe some of these procedures are blocked out there. My apologies for that. I'll try to maybe edit the slides if there's any questions about that. Hopefully it's not too bad. All right, so 7 sets of readings. Once we have 7 sets of readings, we're going to plot a graph of time squared versus the length of the string L, very similar to how we did the pendulum lab 2 weeks ago, and this time we're going to be using those average values for time squared. Draw a best fit line through the trend in the data and determine the slope, right? So remember, find 2 points that aren't data points that are on your best fit line, and they intersect the gridding of your graph paper, which allows you to read their coordinates off and then do a slope calculation. The rise over the run, the difference in the y values, which are the time squared values, divided by the difference in the x values, which are the length values for this experiment. Now, theory suggests that the time of oscillation for a pendulum is equal to 2 pi times the square root of the length of the string divided by the gravity field strength, G. So we're sort of utilizing that equation in order to determine the local gravity field strength, G. By rearranging, we can conclude that G will equal 4 pi squared divided by the slope of our best fit line. So once we know the slope of the best fit line, we can set that equal to sort of the term in the equation, which states how does the length of the string vary to give us the time squared. And just some algebra with that equation of what theory suggests. And hopefully this, will become more clear on the subsequent slide. So as with all of our lab work, we want to claim statement, an evidence statement, and a reasoning statement. The claim will be, what do you calculate g to be in meters per second squared? What is the acceleration due to gravity here on Earth where we're doing this experiment? The evidence will be your graph, with all of the data that you've plotted and collected. The data table itself is also evidence, but once it's on a graph, we can sort of see all of that data there. But indeed, the data, see data table, see graph, right? The data you collect is your evidence. And then there's some reasoning here, and try to elaborate on the experiment in your reasoning statement. This is sort of where you get a chance to explain the experiment. You can critique the experiment in the reasoning statement if you'd like to. But you always sort of want to begin a reasoning statement with, well, because theory suggests the time of oscillation is equal to 2 times pi times the square root of L over G, then I should be able to, measure some various lengths of L, measure the time of oscillation, and calculate the time squared and sort of deduce how that quantity varies against the other one. And so if theory suggests this, then we can collect some data, plot a graph of it, and calculate what the slope is, and then set it equal to the term 4 pi squared over g, and then solve for g. So you're really just trying to think through the lab there. Let's think about it sort of like this. We know from math class the equation of a line, y equals mx, where m is the slope. It tells how x sort of varies to give us the output y. So for this experiment, once you square everything, because we don't want to really work underneath the radical, we find that time squared is equal to 4 pi squared over g times L. So by plotting a graph of L on the x-axis, the length of the pendulum string on the x-axis, against the time squared, those values that we'll have to calculate, from the data we collect, on the y-axis, then we can, using our graph, calculate what the slope is, right? We'll have all of that data we've collected plotted, we can draw a trend line, and we can use the graph itself to determine the slope, to see what value it is that tells us how L varies to give us t squared. And so by deducing m, the slope, we set it equal to 4 pi squared over g, and at that point, we've got a number for slope, we've got, 4 and pi are just numbers, and so we're able to calculate g, and that's going to be our claim. We're sort of saying, well, if this equation, if this theory is correct, then we should be able to use it to determine the local gravity field strength, local g, right, the acceleration due to gravity here on Earth. So you're going to start, you've collected all of your data, you've done all the calculations with the uncertainties, and you have a record of all of that in your journal, and you go to make your graph. Always be sure that we're going to construct some coordinate axes and label those axes with both the quantity on the x-axis for this lab is going to be length, and the units that we're measuring it in, meters. On the y-axis, the same thing, the quantity times squared with the units, seconds squared. Scale your axes reasonably. Use most of the page. Okay, so you want to use most of the entire page with just adequate space in the margins so that you can label your axes. But then really, well more than half the page should be your actual data that's graphed. So then you go and you start plotting your points there. You should have 7 data points, and you'll find that they should fall into a trend. So you can draw a trend line, right? A best fit line that's sort of using your judgment to say, sort of where's the one line that represents the trend in the data, right? You never want to connect the dots because then you have a bunch of different lines. So you're drawing a single line that represents the trend in the data. You want to have about as many points above as below the line. Maybe there are some points that fall on the line of best fit. So those are just sort of some good rules of thumb as you're drawing a best fit line. And then once you've drawn your best fit line, you want to sort of scour that line and try to find points like these, which intersect the gridding of your graph paper, right? And so I can sort of read off the coordinates from my well-scaled axes, and then I'd be able to do a slope calculation, right? Where I have the coordinates, x1, y1, and x2, y2. And then the difference in the y's, or the difference in the time squared values in this case, would give us the rise, and the difference in the x values, the difference in the length values for this experiment, would give us the run, and rise over run is the slope. Once you've got the slope, you set it equal to 4 pi squared over g, and solve for g. That's your claim. Is there any questions about this week's lab? please don't hesitate to ask as always. And we'll be sure to go over plenty of practice problems related to principle of moments, moment of force, and torque of a couple to further elucidate those ideas.